This is Math 139, Section 2.4. We're going to be looking at solving equations that contain higher order polynomials, something more than a quadratic. We'll start with examples that are factorable polynomials. And in all of these cases, we want to make sure we start by setting by setting the equation equal to 0, and then setting each factor equal to 0 separately. But it is really important here that we begin by getting our equation to equal 0, just like we did when we were doing the quadratics. All right, our first equation is not right now equal to 0, so let's go ahead and subtract these two terms to bring them over to the left-hand side. We'll now use our factoring strategies and say that since we do have 4 terms, the factoring strategy we would want to apply is grouping. And so I'm going to group these and those. In the first group, I can factor out a 3x squared, which leaves me x plus 1. In the second group, I'm going to factor out a negative 5, which also leaves x plus 1. That's equal to 0. And then I've got the x plus 1 as my common binomial. I'll factor that out, which leaves us 3x squared for the first term and a minus 5 for the second. Now we want to set each factor separately equal to 0. So x plus 1 equals 0, or 3x squared minus 5 equals 0. This one gives us a solution real quick, just x equals negative 1. But this one, we would have to do a little bit of work. Let's add the 5 over, and then divide by the 3. If that's x squared, x would be the plus or minus the square root. And I'm going to separate those, the square root of 5 over the square root of 3. And then to finish simplifying, I'll just multiply top and bottom by the square root of 3, giving me x equals plus or minus the square root of 15. And in the bottom, square root of 9 would just be 3. So notice this time we actually got 3 solutions. Negative 1, positive square root 15 over 3, and negative square root 15 over 3. Let's try another one. In this problem, we actually have a 4th degree polynomial, x to the 4th plus 7x squared minus 18. It is a trinomial, meaning that product and sum is our usual technique. 3 terms. Oh, and I should have pointed out, it's already equal to 0, so I didn't have to do that. X to the 4th could be x squared times x squared. And then I would be looking for a sum of 7 and a product of negative 18. Thinking a 2 and a 9 there. We'll make the 2 negative, and that way it adds up to a positive 7. So minus 2 plus 9. All right, now that that's factored, I can set the factors equal to 0 separately. This first one gives me x squared equals 2. So x would be plus or minus the square root of 2. And the second one says x squared equals negative 9. So x would be plus or minus the square root of negative 9. Because of the negative under the radical, that's an imaginary answer, 3i. So notice this time we actually got 4 solutions. 2 there and 2 more there. Are you starting to notice a pattern at all? With that 4th degree polynomial, we have 4 solutions. Let's keep our eye on that. All right. The next problem, x cubed plus 27 equals 0, is once again already set equal to 0 for us, so we don't have to worry about that. We just need to factor. And if you notice, this 2-term or binomial is a sum of perfect cubes. I'm just going to remind you of the sum of cubes factoring formula. It looks like this. And in our particular case, the a would just be x. And since 27 is 3 cubed, b would be 3. So my factored form, a plus b, is x plus 3, times a squared is x squared, minus a times b, 3 times x, plus b squared would be 9. All right, we follow our typical rule here. If the product is equal to 0, we can set the factors separately equal to 0. And this one gives us a solution right away. X equals negative 3. This one, however, requires a little bit of work. Notice here, with a trinomial, I might start thinking about sum and product. A sum of negative 3, a product of 9. But I don't think I'm going to have any luck with that. 1 times 9, not going to work. 3 times 3, not going to work. No way to get a sum of negative 3 out of that. So when factoring doesn't work, this is typically where we fall back on the quadratic formula. So let's see. b would be negative 3, so the opposite of b is 3. b squared is negative 3 squared, minus 4 times our a, which is 1, times our c of 9, over 2 times 1. Under my radical, I have 9 subtract 36. That's negative 27. So it looks like we're going to have some imaginary answers here again. Let's see, if I think of that as the square root of negative 9 times the square root of 3, this would be 3i times the square root of 3. All over 2. Or typically when we have imaginary numbers as answers, we write them in that special form. The real part, which is 3/2, plus or minus the imaginary part, 3 square root 3 over 2, times I. All right, so there's our 3 solutions, 2 of them here and 1 more there. And notice that came from a cubic equation. So once again, hopefully we're kind of starting to make some associations there. All right, let's do one more example, and then we'll talk a little bit more about that, what you're probably noticing. The next problem does need some simplifying before we can start to try to factor. I will go ahead and multiply out over here, 2x to the 4th. Plus 6x cubed. And then we do want this equal to 0, so I'm going to subtract the 3x squared to bring it over. Now my polynomial is equal to 0 and even written in descending order. I'm going to notice on this one I've got a GCF. I could factor out an x squared. So I'm going to do that right away. And that's going to give me 2x squared plus 6x minus 3 equal to 0. That means x squared equals 0, or 2x squared plus 6x minus 3 equals 0. X squared equals 0. Just taking the square root, x must be 0. And over here, once again, I might start thinking about maybe a sum and product. Let's just check and see if it would work. We'd need a sum of 6 and a product of negative 6. And once again, I don't think there's any way I'll get that. 1 and 6, 2 and 3, no way to get a sum of 6 on that. So we'll go back to our quadratic formula. Minus b, is negative 6, plus or minus the square root of 6 squared, minus 4 times 2 times negative 3, over 2 times 2. Under my radical, I've got 36 minus a negative is going to be plus. 8 times 3 is 24. Looks like I got 60 under there. I'm going to break down that 60 as the square root of 4 times the square root of 15, or 2 square root 15. Over 4. And I'll notice that all 3 of these numbers are divisible by 2. So it's okay to divide by 2 over 2. It's just a form of 1. It doesn't change the value. And so I might write this as negative 3 plus or minus 1 square root of 15 over 2. All right. At this stage, we've got 1, 2 answers here, plus another one there. That's 3. But does that kind of upset you when you think about what we think we've been developing? I got 3 answers, and this was a 4th degree polynomial. If you were starting to think that the number of solutions should be the same as the degree of the polynomial, you are correct. It should. Here's what happened here. Because this was x squared equals 0, technically speaking, that's x times x equals 0. And if I separated my factors, I'd have x equals 0 or x equals 0. In other words, I get the solution x equals 0 twice. This is going to happen anytime you have a square on a particular factor. Or it could even be 3 times or 4 times that you'll get the same solution. When that happens, we really only list 0 as a solution once, but we kind of reflect the fact that it really occurred twice by saying this is a solution or a 0 of multiplicity 2. So, if I think of the fact that really there were 2 zeros there, plus 2 more solutions for the plus and minus there, now I can see those 4 solutions that I kind of expected for this 4th degree polynomial. We'll sum that up a bit on the next page. Did we notice a connection between the degree of the polynomial and the number of solutions or zeros that we found? Yes, the degree was equal to the number of zeros or solutions when the equation equaled 0, counting multiplicity. So if an answer occurred twice, we had to count it twice, even though it was the same answer. This is really the background for a theorem called the fundamental theorem of algebra, which says that a polynomial function of degree n has exactly n zeros, counted with multiplicity. Now these zeros may be real numbers. They may be imaginary numbers. Or they could be a mixture of both, right? There's some real and some imaginary sometimes. So it's called the fundamental theorem of algebra, and it's probably our very first really big theorem that we've had. All right, we'll continue in the next video.